Just a little bit more about myself. When I was working, I was a functional group manager that did digital design. We did some very complex PC board designs and FPGA designs. I was also a project manager on several multi-million-dollar programs where we had software engineers, mechanical engineers, digital engineers doing some very high-tech stuff. So I had no time for ham radio. When I retired, I was able to spend plenty of time with ham radio, and I always liked good bang for the buck. And I somehow got interested in antennas, and I was looking at what could be done with simple low-cost wire antennas, and the end-fed half-wave was one of them that I looked at in depth. My home station over here just has two end-fed half-wave antennas. One is on 80, one is on 40. They're at right angles to each other. They're no more than about 30 feet high at their maximum height. And I'm not very high up over here. I'm maybe 100 feet above sea level, something like that. Nothing super great. But do they work? Well, I would say take a look at Ham Dash. Go on Google, search for Ham Dash, which is an N3FJP leaderboard type program, and look up K1RF and the New England QSO Party for 2024 and see how I did, just using end-fed half-wave antennas and 100 watts. Okay, this next slide is one of my favorite slides, but people are always looking for a simple wire antenna that's low cost, easy to build, easy to deploy, with great performance from single band to multi-band. And there's actually a few antennas that do come close to that ideal. One thing that needs to be considered with wire antennas is how do you really want to use them? One size does not fit all. They're very operation dependent. For home use, they could be semi-permanent. You could take some time putting it up, and you're limited by what trees are available to you, mounting options, what bands and modes do you want to operate on, etc. Field day needs to be a moderately quick deployment. A unique problem with field day is that you typically have very close located setups where interference is an issue. So there are things that could be done to minimize interference between co-located setups by using, say, a vertical and a horizontal for two different stations and things like that. Talks on the air, got to be portable, lightweight, and very quick deployment. I know some people that go to half a dozen parks a day, even more than that are big POTA operators. Summit's on the air. The antennas have to be very portable and lightweight, as well as quick deployment. And DXpeditions, the antennas have to perform well with moderately quick deployment. So the environment that you're using these in has a big effect on what antenna you can use. Let's talk about end-fed half-waves compared to other antennas. What's the advantages of them? Well, they have lots of advantages. They're very easy to install. You just need one single high point. You could put a low point for the transformer near the ground or on a short pole. You could have many different configurations to suit your installation. It could be horizontal, an inverted V, inverted L, a sloper, which is a favorite of Parks on the Air folks, an inverted U, a half square, etc. There's no hanging feed line because the feed line is off to one side. That's a big advantage for a lot of installations. You need almost no ground system or counterpoise. The coax could act as a counterpoise with or without a choke balun. It's resonant on multiple bands with low VSWR. You could operate, if it's an 80 meter end fed, on all the bands 80 through 10, with only a touch-up tuner, like a 3-to-1 tuner, which you can typically find in the 100-watt rigs. Because of the relatively low VSWR, you have reduced coax losses, and you only have one simple length adjustment. Once you set that, you're pretty much set on all the bands with low VSWR. It's grounded at DC. That's a big advantage. There's no static buildup. A lot of antennas will have static buildup and actually get little spark discharges, but the end-fed half-wave is inherently grounded. You could also make shorter versions for limited areas, and I'll talk about that a little bit. Now some information about half-wave antennas. A half-wave is a radiating element with an electric length of 1/2 wave. It's approximately 468 divided by frequency, gives you the length in feet. But its feed point affects its impedance. It has a high current, low voltage at the center, and a low current, high voltage at the ends. A typical half-wave antenna is the old center-fed dipole. Its impedance is about 72 ohms, basically a monoband antenna. You could possibly use a third harmonic, like a 40-meter dipole on 15 meters. If it's off center fed, let's say, for argument's sake, the 29.7% point, which works well as an 80-meter off center fed and a multi-band antenna, its impedance is about 200 ohms and also can be used on multiple bands. It needs a matching device such as a 4-to-1, what's called a hybrid balun, which is a 4-to-1 Ruthroth balun cascaded with a 1-to-1 choke or guanella balun. But that's a 200 ohm impedance now. The end-fed half-wave has a much higher impedance. It's in the 2,000 to 4,000 ohm range. And it requires some sort of high impedance matching device, which is typically a 49-to-1 impedance ratio transformer or a tapped parallel resonant circuit, also known as a Fuchs antenna tuner. But you need some kind of high impedance matching device. Now, for multi-band operation, it turns out that if you start with an 80-meter antenna, and say it's near the low end of the band, 3.57 megahertz, it turns out you will get multiple harmonics falling exactly on all the bands you want, 40, 30, 20, 17, 15, 12, and 10. So it theoretically can work on all those bands and give you a low VSWR. However, reality strikes and the harmonic relationship is not quite there and requires additional components, and I'll talk about that a little bit. This is a typical unbalanced to unbalanced transformer used for end-fed half-wave antennas. It's typically a toroid or a stack of toroids wound with 2 turns on the primary and 14 turns on the secondary. And those 2 turns are twisted together for the primary and secondary. That's a classical way these are made. They could be made with what's called a crossover. The crossover provides mechanical separation of the output side from the input side, which is good because you want to minimize capacitance between the output and input. Also, what happens is when you're halfway up the transformer, the phase is considerably out of phase with the primary over here, and that causes effectively a larger effective capacitance. So by doing this crossover, you're separating these windings from these windings, and further reduces effects of capacitance. Another way to wind it, which is commonly used, is an auto transformer, where you just have one continuous winding and you tap into the second turn. And both of these can work efficiently. The auto transformer theoretically is slightly more efficient. However, that's only true for transformers with relatively low turns ratios. If you have a high turns ratio, 2 to 14, excuse me, it's the efficiency is almost the same as a classically wound transformer. The toroids themselves typically use type 43 material, which is a ferrite, or type 52 material, which is also a ferrite, which has some different characteristics. And I'll just say, a lot of this talks about building homemade stuff. If you want to, you could buy a ready-made end-fed half-wave antenna or a ready-made transformer. I also want to point out that this is a resonant antenna. This presentation doesn't really talk about non-resonant end-fed antennas, where you just take a random piece of wire and take, say, a 9-to-1 transformer to drive it. That type of antenna is good for emergency use. You could take any old piece of wire and get it working, but it does need a wide range antenna tuner. The resonant type end-fed half-wave has a low VSWR on multiple bands. So the typical built-in 3-to-1 antenna tuner that you find in most rigs nowadays works fine without needing a high-performance antenna tuner. Okay, this slide shows basic end-fed half-wave antenna construction. The dark blue boxes are the main items, as well as a piece of wire. You have a rig driving a piece of coax, driving the transformer, which is typically grounded with a ground rod, and you need some sort of optional counterpoise. The coax itself can be made into a counterpoise by adding a choke balun or a guanella balun. And you pick this length of coax such that it's 0.05 wavelengths long on the lowest frequency of operation. And when you do that, it's non-resonant on all the bands. You want it to be non-resonant because a quarter wave is a low impedance. That's good for a counterpoise. But if it's a half wave, that's bad because a half wave has a high impedance, so it won't act much like a counterpoise. So if you use 0.05 wavelength, it pretty much makes sure you don't have a half wave at the highest frequency of operation. The other optional component is a compensation coil, which I'll talk about in more detail later. And that basically puts all the resonant points closer to where they belong and cancels out the effective end effect. Because if the 80-meter antenna, for example, is tuned for resonance on the low end of the band or slightly below it and below the low end of the band, the upper bands will all work nicely, but not 80 due to end effect. End effect is essentially the high voltage, low current at the antenna ends couples into the ground fairly easily through that very low capacitance of the antenna to ground. And it makes the antenna look effectively longer, but that only happens on the lowest frequency of operation. So the compensation coil tries to correct for that, essentially. Now, counterpoise, that causes a lot of discussions. Do you need one? Do you not need one? What's good? What's bad? The bottom line is you're driving the end of an antenna, and it needs some way to provide for return current. The return current will go somewhere, whether it's in some controlled manner or whether it's not in a controlled manner. If you don't specify one specifically and do nothing special, the coax shield will act as a counterpoise. The problem with that is, without doing anything special, it will have a pretty high common mode current flowing on the outside of the coax shield. And that couples into everything very easily, especially if the antenna is close to your operation point. If you have a 0.05 wavelength section of coax with a choke balun, that minimizes common mode current on the coax going into your rig. So that's a good way to go, and it gives consistent results. People always complain, hey, I made a counterpoise out of a piece of wire, or I'm using my coax, and mine doesn't work good. And someone else with the exact same antenna, they're getting great results. It's all because of differences in the counterpoise for the most part. You could use a wire fence for a counterpoise. That makes a great counterpoise. If you have a vertical at your station, you could make use of the vertical's radial system as your counterpoise. That'll work well. Current to a real counterpoise will distribute itself between a counterpoise and a coax. If you have a coax plus other counterpoise mechanisms, the currents split up. But you want to try to minimize currents on the coax shield because they couple into things in a not nice manner. Is a choke balun needed? Depending on the quality of your counterpoise, current splits between the counterpoise and your coax shield. A lot of people don't want to bother with a common mode choke. I'm an advocate of them. It could be used either right at the rig or using a section of coax, which acts as a counterpoise. You could make one out of a high power one using an FT240-31 with 12 turns of coax, like RG 400 coax. That can handle high power. That works very well. I built several of those. The only problem is your RG 400 is like a snake. You have to really work at winding it on the choke, the toroid. You could heat it up with a heat gun, and that'll help a little bit in trying to wind it. But it's really a bear trying to wind that on the FT240. For a 100-watt rig, you could do something different. You could make a really cheap choke balun out of a 12 version of an FT114-43. It costs a big $1.78, quantity of one, and use a length of RG 178B, which is a small diameter coax. This is about 97% efficient, and the toroid itself can dissipate about 3.5 watts. Very efficient, greater than 97% efficient. So you could actually run FTA digital modes, 100% duty cycle at 100 watts, and this little choke balun could take that power. It also performs well. You could make it out of either two FT114s, which are kind of standard toroids, or a single 12 version, which I list the part number here, the ferrite part number. And I listed the ferrite part number for the FT114-43. It's a great little choke balun for 100-watt rigs. Now let's talk about ferrite materials a little bit. The most commonly used ferrites for end-fed half-wave transformers are type 43 material and type 52 material. Type 43 has a pretty high, what's called permeability, about 800. Ferrite is much lower, 250 permeability. And 61, which I recommend not using for most people. You're not going to get good results with it unless you really know what you're doing. It's 125 permeability. The 43 is good for lowest cost and low power rigs. The type 52 is best for multi-toroid high power. These have what's called a higher Curie temperature. The Curie temperature is the temperature at which the ferrite loses its magnetism. You might as well be wound around a piece of wood instead of a ferrite. People constantly put too much power into their transformers, and then they just stop working, and the VSWR rises, and they wonder why. Well, it's because they're putting too much power into the toroid. But this does give some safety margin. But even around 150 degrees Fahrenheit, you start melting the case. So the type 43 still works fine and could get quite hot and start melting your case before it reaches the Curie temperature. Another point is never use powdered iron cores for an end-fed half-wave. Oh no, they just don't work. The permeability is way too low. Okay, then what's the compensation capacitor? A lot of you may have seen in either homemade or commercially made transformers, there's a compensation capacitor across the primary of the transformer. What's that for? I had no idea when I first was learning about these end-fed half-wave antennas. Basically, the transformer has a high amount of leakage inductance. Leakage inductance is inductance that doesn't go inside the ferrite. It goes outside into the air, basically, and it degrades performance. When you drive an antenna at resonance, the antenna looks like a resistance. So you're driving what looks like a series L shunt R, which is a low-pass filter. Well, guess what? A low-pass filter starts reducing RF through it when you reach the frequency of low pass that it's happening at. What the capacitor does is it attempts to convert the leakage inductance into a lumped element transmission line where 50 ohms equals the square root of the leakage inductance divided by the capacitance, compensation capacitance. Value is not very critical, but it improves the high frequency performance by sort of absorbing that leakage inductance into a lumped element transmission line. That's basically what it's doing. It's very important for that capacitor to have a low ESR, or equivalent series resistance. The thing that kills those capacitors is not overvoltage. It's overcurrent with a capacitor that has excessive equivalent series resistance. A lot of people use these blue caps that you could buy on eBay, and I've used them. They generally work, but their equivalent series resistance is not specified. I would recommend, at least for 100-watt rigs, KMET makes a 100 picofarad C0G NPO capacitance, 5% tolerance and 3 kilovolts. Costs $2.41, or $2.12 at Mouser. It's low ESR rated. There's another capacitor which a few people are using now that are in the end-fed half-wave, the real end-fed half-wave antenna Facebook group. That one only costs 45 cents, made by TDK. It's not a NPO COG capacitor. It's called SL. Dielectric is SL. It's somewhat like C0G NPO, but it's a different type of dielectric. If you want to be conservative, buy the more expensive capacitor, but these should work. I haven't used it myself. I have used the KMET capacitor, and that works. For high power transformers, probably want to use a doorknob capacitor. Those can handle high current, but they're not cheap. They could cost like 15 to 30 bucks or something like that. And just a few numbers here. At 100 watts, the rating of the capacitor is only 446 volts, even with a 5-to-1 VSWR. At a kilowatt, though, the peak voltage with a 5-to-1 VSWR is 707 volts. And with 50% derating, it goes up to 1.4 kilovolts. 1.4 kilovolts is still not really very high, but the current can be pretty high. Let's say, for example, the current through the capacitor is 1 amp. It's kind of hard to tell what it is because it's part of the compensation network and currents divide all over the place. But let's say it's an amp RMS. And let's say the capacitor, not the capacitor, yeah, the capacitor has an equivalent series resistance of 10 ohms. 10 ohms doesn't sound like very much, but 1 amp with 10 ohms, I squared R, it's 10 watts. You're dissipating 10 watts in a capacitor. So for high power, you really have to pay attention to low equivalent series resistance. Okay, here's the compensation coil. You could make your own. It's about 1.5 microhenries. You could just wind 6 turns on a 1 1/4 outer diameter inch PVC form, position 78 inch from the feed point, whether it's 80 or 40 meters. Steve Ellington, who used to run a NFET half-wave antenna Facebook group, has a YouTube video on it. It basically lowers the resonant point more and more as you go up in frequency. So it works pretty nicely, especially if you're operating on sideband. It's not absolutely necessary for an antenna. You have an antenna tuner to compensate, but it gives better performance in general than without it. Okay, let's take a look at VSWR plots on a real antenna versus a resistive load. You could use a resistive load to test your transformer, and typically it may slowly rise, or you may have a little dipsy doodle over there. But when you put a compensation capacitor across the primary, the whole curve will generally go down, and it'll tend to be much improved on 10 meters. The curve is really a function of a lot of things. The number of turns on the toroid, the ferrite type, the efficiency of the toroid, the leakage inductances, self-capacitance, et cetera, So these will vary from transformer to transformer, but the compensation capacitor definitely helps. A strange thing I learned, though, is when you feed a real antenna with a transformer, instead of just a resistive load, the VSWR can actually improve. This is a plot I made from one of my antennas, and the VSWR can be pretty low. So how can it be? It makes no sense at all, right? Well, what's really going on is the antenna is cut slightly short. When it is cut slightly short, it looks like a resistor in series with a capacitor. It looks slightly capacitive. The slightly capacitive impedance cancels out some of the leakage inductance inherent in the transformer, and it makes the bandwidth wider, and it makes the match better. So you can get a lower VSWR with a real antenna compared to a resistive load. Counterintuitive though it sounds. Now, there is a problem that I alluded to earlier. If you try to make this antenna work well on all bands, the 80-meter resonant point is probably going to be too low. It's going to be either right at the edge of the band or in the CW region. And if you want to operate on sideband, it's going to be way off. The way to fix that is to add a capacitor at the middle of the antenna wire, shunted with a resistor to bleed off static buildup across the capacitor. For a 100-watt rig, it just has to be a kilovolt. It's very conservative, with a say a 33K 2-watt non-inductive resistor placed across it. If the initial resonance was at 3.5 megahertz, a value of 470 picofarads will raise the resonant point to about 3750. And you could make that capacitor smaller than that if you want something between, say, 3.5 and 3.75. Again, Steve Ellington had a YouTube video on this, further information. But that way you can compensate for the resonant point on 80 and put it essentially any way you want it and have almost no effect on the higher bands. You shorten the antenna by using a inductor towards the end. This comes from PA1ZP in an RSGB article. Basically, the antenna, a 40-meter antenna, instead of being about 66 feet long, it'd be more like, let's see, 40 feet long. And an 80-meter antenna will be, let's see, 70 and 7, about 80 feet long compared to 130 feet. The only disadvantage of this approach is it's going to become more narrowband. So it may be a little trickier to tune, and you may need a wider range antenna tuner if you want to cover the full bands on all the bands. They become more narrowband, but it's a usable antenna for people with limited antenna space. People build these and they work. You can add 160-meter capability if you want to. Use it like a quarter wave. Switch out the transformer, have some sort of real counterpoise for it, like some ground radials, and then you could be on 160 meters. Steve Ellington has a YouTube video on it where he can switch out the transformer remotely and give you 160-meter capability. On the housing itself, a sealed box will have moisture and pressure buildup, so you got to relieve that. The simplest thing to do is drill 2 little holes on the bottom of it. That's basically what I do on mine. It works fine. If you want to get fancy, and some of the folks like My Antennas sells these with a air vent, which is a fancier way of implementing that. It's very good for pressure relief, as well as give more venting. But you could always drill bigger holes and put some non-metallic screening in those holes if you want more air circulation. But this costs about $4. Okay, getting back into the technical realm on end-fed half-wave transformers, and I've simulated a lot of these using this tool called SimNet. It's a free program, but I've done a lot of simulations of transformers. The inductance of the primary is very important. These transformers have to work over a 10-to-1 frequency ratio with a very high turns ratio, and those together mean that the transformer is a compromise. If the primary inductance is too small, you're going to start loading it down and causing a VSWR increase. If the primary inductance is too high, on the other hand, the performance will suffer at the high end due to increasing leakage inductances. I made a rough rule of thumb, which you should try not to exceed. The primary inductance should be in the 88 ohm to 200 ohm range at the lowest frequency of use. This turns out to be about 4 to 9 microhenries on 80 meters, or 2 to 4.5 microhenries on 40 meters. Many of the commercial transformers don't meet this, and they work poorly at one end or the other. Also, inductance increases with size of the toroid and number of toroids. If you have 2 FT240s instead of 1, you're basically doubling the inductance. And there's a nice website, toroids.info, where you can put in commonly used toroids and number of turns, and it'll tell you what the initial inductance is. That's a real useful tool. Here's a table that you won't see too often. I computed how much power can toroids actually dissipate before they overheat. So I took a whole bunch of commonly used toroids and toroid stacks and computed their power for a 150-degree Fahrenheit rise above ambient, or 25 degrees. Excuse me. And these are all the powers. I estimated the efficiencies here, but you really should measure them. And then the power input is simply the capability of the toroid's power dissipation divided by the duty cycle with efficiency taken into account. So for CW, which has a 44% duty cycle, you could do quite a bit better than digital modes, which are shown here. For sideband, you could do even better, assuming 20% duty cycle. For the high power one, which is 3 FT240-52s, you could run about 900 watts on sideband. You'd probably do a kilowatt. 20% efficient duty cycle was conservative. So you could probably get about up to a kilowatt with the biggest type transformer. But you definitely cannot run a kilowatt on CW and only 180 watts with digital modes. So people abuse the power on these things all the time. Here's what I would use for a 100-watt homemade toroid. This is a particular part number of ferrite. It's sort of a short, stubby toroid, chunky. I like to call it chunky compared to the conventional, like the FT240 type. It's very efficient from a inductive standpoint. You need fewer turns to get the same amount of inductance, which means you get lower leakages, lower leakage inductance. This is wound as an auto transformer. There's a little compensation cap. This is better than 90% efficiency. And it could dissipate 7 watts. So it could dissipate 70 watts continuous, 159 watts on CW, 350 watts on sideband. And it costs about $8.13. Just one comment on 10 meters. Think about making a dedicated 10-meter antenna instead of trying to use the 80-meter end-fed half wave if your transformer is inefficient. It eliminates the transformer entirely. So you could run high power with it, no worries with high power. It only has to be 16.5 feet above ground for a half wave height, which will give good performance. It has 7.9 dBi gain and has a decent takeoff angle with known directional pattern. An end-fed half wave on 80 meters, it'll have multiple lobes on 10. Multiple lobes could be okay, like for field day. If you don't work one guy, you'll work another guy in a different direction. That's okay. But if you're trying to work DX and you want your antenna to radiate in a certain direction, a dedicated dipole works very well. Here's a list of common errors in building homemade transformers. Never use powdered iron cores. You got to use ferrite. Don't use 61. Use 41 or 52. Doesn't need insulating tape. In fact, insulating tape degrades performance. You're making an air gap over there, and the air gap increases leakage inductance. In addition, ferrite toroids of at least type 52 and 43 are high impedance. You're not going to short circuit anything with them. Even if you have a nick in the wire, it's the ferrite is an insulator. It's easy to count wrong number of turns. One turn is defined as passing through a hole inside the toroid, including if you have a crossover turn, that counts as one turn. And you don't want to run these near a tower. If you want to use an end-fed half wave off the tower, put the transformer at the top of the tower, not at the base where the antenna is running next to the tower. It's just going to work really poorly. Don't put the choke balun, if you're going to use one, right next to the UNUN. If you do, you're not trying to make use of the coax at all, and it'll just find a straight path for the return current, which you don't want. There's also a lot of confusion about impedance ratios. An end-fed half wave needs a 7-to-1 turns ratio, a 49-to-1 impedance ratio. A 4-to-1 is good for off-center-fed dipoles. A 9-to-1 is good for random wire, non-resonant end-fed antennas. And the big no-no that people do all the time is putting too much power into an undersized or inefficient UNUN. So you gotta be careful about that. If you want to buy a ready-made one, I recommend my antennas. They know what they're doing over there. Their transmission line, I'm sorry, their transformers are very efficient for end-fed half-wave antennas. They're greater than 90% efficient typically. For QRP, you could use a Fuchs type tuner, a parallel resonant circuit with a tap on it. QRP, guys, makes a nice one that covers 40 to 15, and it has a built-in VSWR bridge for tuning up your rig. So those are what I would recommend. The ARRL sells an end-fed half-wave antenna kit. What I would say about it is it's good quality components, easy to put together. It's rated for 250 watts PEP. Talking about sideband there. Good instructions, but it's fairly inefficient. It has about a 1 dB loss on 20 meters, which is about 80% efficient. On 10 meters, it's pretty bad. It's 71% efficient. If you want to build it, I would recommend adding another FT240-43 to the mix, or use that other transformer that I showed. But this has the advantage of you could use an 80-meter wire. The power is a little bit more efficient, and whatever is dissipated is split among two toroids, so that each toroid is seeing a much lower power dissipation. So it'll run much, much cooler. So that's some things to think about there. If you're not going to use it on 10 meters, you're probably okay with a 100-watt rig. I wanted to include this. End-fed half-wave versus off-center fed dipole. The end-fed has more flexible mounting provisions. You don't have a piece of coax hanging down from the middle or offset from the middle. It's inherently grounded. Its main problem is that it's difficult to make a high power efficient transformer. It's also fairly expensive. The off-center fed, it uses transmission line transformers. For a given power dissipation, they're much lower cost, they're much smaller and cheaper. These could be 97, 98% efficient easily, whereas the end-fed half-waves, the transformer is more like 90% efficient for a good transformer. It has less flexible mounting provisions because of the coax hanging down from it. And it's hard to find commercial good hybrid transformers. You're better off building your own. There's a off-center fed dipole Facebook group with a whole bunch of data there. Tells you how to build your own. And this last thing, I just was listing sources of parts. The box you could get at a Home Depot or a Lowe's. You could buy Amazon for wire and for stainless steel rope clips at the top if you want to have that. And other miscellaneous parts. So it's not that difficult to get the parts, but you're better off getting a whole bunch of people together as a group to save on shipping costs. And then at the end, I listed some resource links on end-fed half-waves. I guess this presentation will be available to you at some point. And you can also look at gnarc.org for other antenna presentations. I put together one on off-center fed dipoles and one on delta loop antennas. And those are all on the Greater Norwalk Amateur Radio Club website. And there's a lot of good data in there for all kinds of wire antennas. And that's the story here.